can go ahead.
Okay. This morning we have the Group A Phase 2 test commencing. This program is being recorded and will be put on our YouTube channel. So anybody who doesn't want to be recorded should leave the meeting. We will start with Q&A. Each of the teams have sent short videos to the committee. The committee has reviewed them, and we'll have some questions here. We'll start with UiS, then we'll go to UMAT, and then to UofC. Then we'll take a break, and then it should be approximately 9:30. We'll start a demo, and we've got 2 hours to complete the demo. It certainly should not take that long. When somebody has their information prepared, then we can see that. We will want you to share some of your screens to show the processing, if there's any intermediate steps. And it's because there's so many people on the call, we're going to ask you to raise your hand before interrupting, and we'll call on you in the order in which those are received. So are there any questions at this point? You're easy. To the committee, are there questions starting with University of Stavanger? Come on, cowards, speak up. I had a question. You do some pressure calculations and you iteratively start from the bottom up. Why do you do that?
The bottom hole pressure calculation, you mean?
Yes.
Yeah. We follow the shielding method. So we suppose that we have a bottom hole pressure at the end of our well, let's say at 2,000 meters. And then we have a liquid flow coming from the mat at the end, and calculating node by node all the way up, dividing the drill string into a number of parts, let's say 100. We create 101 nodes. For each node, we calculate the pressure all the way to the top. And when the pressure at the top coincides with the atmospheric pressure, according to a tolerance that can be set up as, let's say, 0.1 bar, that's when our iteration finishes, and that's when we stop updating the downhole, bottom hole pressure.
Okay, and well bore diameter is bit diameter?
Yeah.
Okay. Come on, guys. Don't leave me here all alone. I don't know enough.
Should we tell you more about the code itself?
In a minute, in just a minute. Okay, my next question is, you have a module that you call reinforcement learning. What is that?
Yeah,
with reinforcement learning, we are doing 2 jobs. One is the application of reinforcement learning in RSS simulator for trajectory control, and the other one is for managed pressure drilling. Both of these parts of the study are the parts of the master thesis of 2 of our, and they are not integrated into RSS simulator yet. That is one of the future works that we intend to do. For the second part of the reinforcement learning, we plan to use it in managed pressure drilling to optimize a PID controller by tweaking its tuning parameters, as well as suggesting a reference BHP to get a stable dynamic response for the controller.
Okay.
Elaborate a little bit more.
So those 2 RSS and MPD models are not currently implemented?
They are not implemented in terms of reinforcement learning, but there is a RSS simulator which with which every other module communicates with, but it is not reinforced with the reinforcement learning yet. That is one of the next steps we have for our future plans.
Oh, okay, okay. But reinforcement learning means what? I don't follow.
Reinforcement learning is the type of learning in which an agent trains itself in environment. In our case, let's say in MPD, the training environment for that's my master's thesis. In this master thesis, the training environment is based upon Open Lab Simulator that is developed by NORS, and the agent, which is a PPO agent, it tries to find a policy with which it can maximize its reward. When I say reward, it means that the most stable response with the least overshoot and the least oscillations will give the maximum reward for the case of MPD. And obviously the best suggestion for the reference bottom hole pressure, which is supposed to be kept near to the pore pressure to increase the ROP. But the concept of reward is defined with respect to the problem at hand, and the agent in reinforcement learning tries to maximize the reward. And the same problem is modeled for trajectory control as well. And reinforcement learning is going to be applied in that area as well, and that is the master thesis of another member of the team.
Here is our reinforcement learning agent is trying to find the best reward and try to converge his understanding or learning rate to the reward. So it will give the best optimized result for the trajectory control. For my case, for my friend's case, it will be for the MPD control.
Good, thanks a lot. You also mentioned learning toolbox. Is that something that you're just using from MATLAB, or did you develop something?
We are using the toolbox from MATLAB, but we developed our environment, like reward environment. The structure of the simulations for me is the RSS, because it needs to communicate with the agent. So it needs to be prepared according to agent, and also reward needs to be optimized so it can give logical results.
Okay.
For example, in the case of the toolbox in MATLAB, it provides us with different agents which can take different actions. In the case of MPD, the actions would be the values of KP, KI, KD, and the reference BHP, which we want to feed to the PID controller. And the toolbox job ends there, and then we have to develop an environment which can take in those inputs and then process the dynamic response, based upon which we will calculate the reward for every action that the agent takes.
Okay, so
in your video presentation, the slides that you sent are not the same slides as in the video, but in the video presentation you had slide 21, and you mentioned something was maintained by NORSA. I didn't follow that.
Yeah, just okay.
One sec, I will pull out the presentation once.
21.
21.
Like I say, it was in the video.
In the video, it's when
Yeah.
you get out. Okay, I will pull up the video when we are exactly in slide 21.
Yeah. But I was curious what you meant, maintained by NORSA. There's something about the data.
Ten seconds.
Okay.
Remember the slide.
this one.
This one, okay. Yeah, we have it here. I'll share my screen.
Yep.
Can you see?
Yep.
So here's the MPV.
In this case, I think when I mentioned Norse, it was for the simulation environment to the left, the red box. That environment runs the simulation for some time. The time we defined was 500 time steps or simulation steps, which is roughly 7.5 minutes. For this simulation is run on the Norse webpage, but the MATLAB communicates with the Norse to run the simulation and takes action from the reinforcement learning agent. The actions in this case are going into the PID controller. These actions are the values of KP and KI, and furthermore, we send the value of the reference value of the bottom hole pressure, the one that we want the controller to achieve. And all of these suggestions are made by the reinforcement learning agent. And we tried different reinforcement learning agents in my thesis. We tried proximal policy optimization, and currently we are working with multi-arm banded problems because we have to give the acceleration just in the beginning of the simulation, so the whole problem can be modeled in that way. But the Norse thing was used just for making the environment.
Is this their drilling simulator, their control simulator in their facility?
Simulator.
Okay.
And then, of course, we fetch the results back to calculate the reward, and then we feed the reward to agent so that it can see whether the actions it took were good or not. And obviously, the goal is to maximize the reward.
Okay. Any other questions?
Yeah, maybe from my side, this is maybe a general question, but you chose a reinforcement learning method. Have you considered any alternative methods, more traditional statistical method or optimization methods?
Actually, we think about that, but the main aim in here, making multiple episodes to see what is the response of the simulator and what is the best possibility for my case to get the best trajectory. Maybe I can show better when I share my screen. For example, this is the background of simulator. So it is picking a weight on with an RPM values during the simulation, like during the trajectory, and actually it is repeating the episodes. So it is changing and finding the best rewards, and the rewards is oscillating actually because there is noises. So the agent is trying to find decide it. We cannot make this possibility with another application because they are not making hundreds of simulation. They are not picking the action, but with the reinforcement learning, it is picking the action. So we can see the reward and we can pick the best option. Actually, we are not picking, but it is picking itself.
And also our purpose is to replace the decision making person or the human individual, whoever makes the decision on the suggested reference points and the tuning parameters used in the episode. So the only way to replace the decision maker is through reinforcement learning, because then an agent takes a decision instead of the decision maker.
For example, there is an example of the this one. This is there is a two path. One is design path, PWP. Another one is designed by the reinforcement learning, and they're almost matching. And the values are here. The weight on bit and RPM values are action from the agent. And as an output, I am getting ROP and the reward. And the ROP is showing around 10 meters per hour. And it is oscillating, so it is close to realistic physical situation. And we are seeing also reward So it is trying to maximize reward or at least stabilize it.
What components do you use to calculate the cost or slash reward?
Yeah, actually, for my case, I can show from here. What I use, I use tool face angle. This is between the points between the RSS, the simulated points, and the given PWP points. And the another one is the rate of penetration. The other one is the dogleg severity. This is causes penalty also, higher than some value. And also reward for ellipse. In this case, I determine ellipse manually, but I am also calculating that ellipse by using the ellipse of uncertainty. And this is the structure of the reward function. So it is if the case is very low, the tool face is very low, it causes very high reward. It is giving error on the my algorithm, so I stabilize it some value. But if it's higher than 0.1, so it calculates a reward. And if it's not inside of the ellipse and the dogleg severity is too high, so there is a 2 penalty. I am adding each other to them. And if it's out of radius, it is giving another penalty, the P2, and it is around 100. As you can see in here, let me show you more clearly. It is a little bit slow. Yeah. For example, in the blue parts are the rewards. So in here, it get almost minus 9,000. So that means they're in the penalty zone, and the agent is trying to get rid of it, and it find the best possibility later on, and it start to find the stable points, and it's almost converged. So it is almost trained. So I can make simulations and output my results.
Are the reward penalties weighted in any fashion? Or are they all equal?
No, they are not equal. Actually, I am trying different scenarios. This is the first scenario, the second scenario. This is the first scenario. For example, I decrease the penalty. When I decrease the penalty, it is the agent is not learning as much as for this case. So I am developing in the same time the reward function right now.
Okay.
These are the current rewards.
So how does the result depends on the value so this value we see here, L1, L2, L3, L4, and P1, P2 strongly affect the results. How your results depend on this choice. This is a choice, right?
Yeah, maybe I can show from here. So this is the agent. So this agent is like the first case it's trained by the first case. So it is not picking easily because it is thinking there is less penalty. So it is thinking I can maybe find a window in that area. I can get better results, but I couldn't get a better result. So I increased the penalty. So when I increased the penalty, it became like a kid. It's trying to get away from that value. So it is trying to find the best possibility. And with the best possibility, I am getting the best optimized trajectory following the PWP, planned project trajectory, and the best ROP. It is not the fastest ROP. If I apply the fastest ROP, for example, in here, this one is very high ROP. It is around 20 meters per hour, for example, but it is not following the trajectory so much. So there is an optimization problem for the trajectory. So this shows there is some loss from the ROP, but you are catching the trajectory. So I am trying to find a sweet spot for this one. And in this case, there is no trajectory control by the RSS module by the PID controller. I am just trying to optimize by the weight on bit and RPM. So later on in the next phase of this work could be controlling the RSS with the PID controllers. So it could be more developed and then modernized.
In the video on slide 23, you show MSE, and then you go from MSE to the rock strength, to the hardness of the formation.
Yeah. One second. Screen. Wait a sec.
At the bottom, you show. So, how do you were trying to classify the formations as your model essentially is drilling them, or do you have those formation hardnesses already as an input that you would then use that to perturb the model, to disturb the model?
No, we're trying to classify the formation after it was drilled by depending on the downhole torque, the ROP and RPM parameters. So by the way, is formation like classified.
Okay. Make a note. That's all the questions I have. Is there anyone else? Okay. Well, we're going to get ahead of schedule today. All right, you guys are off the hot seat. You can relax a little bit. All right. Who's here from UMAT? Anybody here from Ghana? Ah, here we go. All right. So I was wondering, how do you calculate the well condition? You talk about well condition in your presentation, but I was a little bit confused on how that well condition is calculated. Did you guys hear my question?
Yeah, I think we can. Yes, so for the well condition, we look at the plan, the well trajectory plan. We take data from the well trajectory plan, and again we take data from we take data from the well trajectory plan. So we use the various.
Excuse me. I guess we can hear you, but there is a strong noise, a strong echo. So could you try, you are connected with 2 different laptops, right?
Yes, please.
Can you make a sign, because I'm not sure I see who is speaking. Ah, okay. So can you open your mic? Yeah.
Yes.
And make
So,
sure other laptops are muted in the same time.
okay. Yeah, so I think I can speak now.
Yeah, okay. Yeah, no, it's getting bad. Now it's okay. Try to. Maybe you have another laptop to try the sound with?
Yes, I think it's still not. Yeah, okay, I think I can proceed now. So with our conditions, we look at the work plan and we also look at the formation characteristics together with the target. So basically what we do is that we pick data from the work plan and we use to calculate the various conditions. So for example, for the work plan, maybe at a particular TVD, we use the inclination to calculate for the target drag at that particular point. And we use it to calculate for other parameters too as well. So that's how come we're able to use our conditions to calculate for the token back to know the work conditions.
And how do you use this in the model?
Pardon?
What does that affect in the rest of the model?
Yes. So what we wanted to do is that we wanted to look at the work condition. That's by looking at the work plan data. Then we get to estimate the highest stock and drag we can encounter based on the work plan and the highest pressure we can encounter. Then we use that to design our equipment.
Okay. And is that used in the initial well planning itself, or is it updated in real time?
Yes, so it's updated in real time.
Okay, great. You also mentioned core elements. So what particular modules do you have in the core elements? You have, you know, a bit-rock interaction, steering. What are the different? You mentioned earlier you have torque and drag. What are all the models that you are using? The modules within your model.
Hello, can you hear me well? All right. Okay, so first of all, by core elements, what we mean is that the main components that make up the drilling process.
Right.
And for us, that's one, we know that we need the drill collars, the drill pipe, we need a bit, and then we need the stabilizers and the steering and control systems. Now, we are from the perspective that you don't just stand up and pick a drill color and a drill pipe. You have to actually design it, and you design it to suit the conditions you're facing. So to make an analogy, if you want to lift something heavy, you have to make sure you pick a tool that can do the job. So we first of all study the conditions of the well, like we studied like what's the torque and drag based on the well path or the well design we have. And then with those conditions, based on the pipe, the drill pipes and the drill color designs available, what pipe will fit for it mechanically in terms of safety and then cost. Yeah, so we design our system to automatically do that, and then select the best pipe in terms of safety, in terms of design and its geometry, and then cost. Yeah,
Okay.
that's the concept.
Okay. All right, so I misunderstood. So from when you're looking at the well condition, you're looking at buckling, torque, etc. And then the core elements are the tools and the rig machine and the drill string and bottom hole assembly. Okay.
Yes, yes.
Okay. All right. So your model includes torsional oscillation. So are you looking at stick slip when you say torsional oscillation?
Yes. So for the torsional oscillation, we are looking at the stick slip. So we're able to consider the stick slip. So as the years go by, we'll update them on that.
Okay, great. All right. And pressure, is this wellbore pressure or something else?
Yes, please, is the wellbore pressure.
Okay. And so how do you calculate, for example, wellbore pressure? Do you show the formulas in the slides, or? I didn't see that. Is it a static pressure plus the dynamic from the pump, or what? What have you done?
So with the wellbore pressure, we calculated it by first determining the equivalent circulating density, which is a function of the density of the mud plus the annular pressure losses over the product of 0.052 times the TVD. And so we first determine the annular pressure losses at the collar and then at the pipe section, and then add it. Okay, so with that we consider the length and then the diameter of the collar for the collar section, and then consider the length and then internal and outer diameter of the pipe and the pipe section to determine its pressure losses. And then after that, then we put it back into the equation to find the equation. And so after that, we put it back into the equation to add it to the original mud density to find the equivalent circulating density. And after finding the equivalent circulating density, then we put it into this formula, 0.052 times the EC, equivalent circulating density, times its corresponding TVD at that particular depth to determine the wellbore pressure at that depth.
Okay, that's good. I'm looking at your slide that has a title called Control System. And do you have it in front of you there? Okay. You show an RSS tool, force on bit, and then you say rate of penetrations. What is rate of penetrations with a plural term?
The rate of penetration, you are looking at the ROP axial and ROP lateral. And to explain further, for the control, mainly we are looking at the control where you start deviating the wall, the drill string, and the ROP here basically means the rate of penetration normal, as in the actuation force produced by the RSS to force the bit to move in a certain direction.
So we kind of adopted the RSS mathematical models used, and then the newer technologies use the concepts from it to model the ROP, the force on bits that will be the force or the actuating force that will be created due to the natural displacement and then the offset. And then we send that data to the bit to get an ROP. Basically find the ROP in the normal direction to the axis.
Normal to the axis. Okay. That's what I thought. Excellent. Okay. There were not many flowcharts or diagrams, so it was difficult for me to try to follow all the pieces in your model. So that would be something that you would want to add and improve in the future. If you have some of those in front of you and wanted to share with us now, it would help. I can't hear anybody.
Yes, so please, we want to quickly open our charts so that we can.
Okay, yeah, that would help a lot.
Yeah, it seems you are having challenges accessing the files, the external hard drive. You are having challenges, so we would like to do that later.
Okay. While you're looking for that, what was it? Well, I found it fascinating that we had two universities working together, and I wish you would kind of tell us, how did that go? Did it work well? Was it difficult? What problems did you have? How did you solve them? What problems were you not able to solve?
Yeah, okay. So I think it was an interesting experience, and coming together as one team from different universities, that's KNUST and UMAT. One of the challenges we had was the issue of coordination. So because we weren't meeting physically, we usually spend a lot of time on the Zoom meeting, and at times trying to communicate something on Zoom is not really clear. So we had to organize so that we could meet. That helped a little bit with the coordination. And again, one of the challenges we had to was support. So that was one of the challenges. But I think apart from that, it was a very great experience having diverse ideas on board to actually solve a problem.
Yeah, just to add to that, I'm from a different KNUST, so from my perspective too, I think we are actually in the same country, but you will also realize that culturally, like, there's a huge distinction between the culture of, let's say, the two universities. So one thing I got to learn is how different our cultures were from the two universities, and how well we merged around, let's say, this certain common values to get the projects done. I think that was quite fascinating. Yeah, you wouldn't think probably from the same country you would be so different in the way you approach things, but it was worthwhile. Yeah.
Well, you also seem to come from two different technical backgrounds. One is studying drilling, and the other one is studying the computer sciences. Was there much overlap, or was that difficult to speak the same language, if you will?
Yes, I think I'm from the petroleum. I have the petroleum background, that's the drilling.
Okay.
And my other colleague has a mechanical background, and the other has an electrical background.
So it is actually mechanical, electrical, and petroleum engineering.
Okay. Mechanical, electrical, petroleum, and what?
Mechanical.
Okay. Yeah. All right. Excellent. Anything you guys want to add? Those were my questions.
Please come again. I didn't get that.
Is there anything that you guys want to add? And that's all the questions that I have.
All right, then I guess this will be a good opportunity to give an angle from where an angle from how we approached the project. So first things first, per the guidelines, our fundamental objective was to think about the best way to design the system to autonomously do directional drilling, but not just do directional drilling, but design. And when safety is the hallmark of everything and human factors are very key, usually you begin from the design stage. That is selecting the right tools for the job. And literally saying that preparing well for the conditions you will meet. So we kind of emphasized our design on our ability to study the conditions. You are like, okay, fine, I'm going to experience 20 megapascal pressure. I need to select, let's say, a pipe that could withstand that. And I need to do that autonomously and I leave the human out of that system. So basically, we would like to achieve directional drilling, autonomous directional drilling from a perspective of proper design safety, the design safety from the beginning, and then eventually we carry it on in the design. So that's the angle at which we approach the project from.
Okay, that's good. I kind of got a question for all three teams if somebody wants to try. When you develop your displays, are you developing the display for normal operations or for, excuse me, or also for abnormal operations?
Yes.
A lot of times we see somebody create their display to say, okay, we're drilling along and we just want to make sure everything is kind of going okay. But if there's a big problem, do you have the information for the driller, in this case you, to actually understand what the problem would be?
Yes, so that's where the feedback system comes in. So we implemented the feedback system in our design that based on the work condition and based on the parameters we have, when you are drilling and you are exceeding your limit, it's going to prompt you that, hey driller, you're exceeding your limit. So there's something you need to put in place, or you need to take in some measures to ensure that you don't actually make your drilling operation very expensive by encountering problems. So basically, that's what we implemented, the feedback system, to keep in check.
Either of the other teams have a comment? Okay, if that's all, then we'll move over to Calgary. Thank you. Who's here from Calgary? I see Darlington and Roman.
Yeah, we're here.
Okay. I have to find my notes. So you have both an RSS model and a mud motor model? You have both?
Pretty much. So in terms of the side force calculations, we used RSS model. And then we have three apps to present today. So the final app is working with the mud model model.
The final that you're using today has which? Just
mod model.
mod motor. Okay, that's right.
But
okay.
the side forces are calculated based on RSS.
Okay, got it. Excuse me. Okay, but my motor today. Torque and drag. How do you calculate torque and drag? Where do you get friction factors and things like that?
So what we did was to first run a torque and drag model on the plan, and then have the several friction factors from 0.125 to 0.4. And so we now use that plan to see if anything is close to buckling limits for the components of the drill of the DHA. And based on that, we are able to know which one is safe, which friction factor is safe for us to use.
Okay, good. Do you monitor any hole cleaning?
No, we don't monitor, but we do monitor. So we do some founder point analysis to make sure that we calculate the optimum ROP. So how we are escaping vibration issues is that using the founder point, that point on that founder point, ROP point, we extrapolate based on the past 10 minutes of data. We extrapolate to get the recommended weight on bed and RPM values at the surface. So that we are fast enough at the optimum ROP, but slow enough so that we don't go into damage to drill string.
Okay. Yeah, I also saw that you have on one graph, you show buckling. So these are compression limits, and then you show maximum tension limits, and then you showed these different calculations based on the operation and what's going on along the line, which I thought was pretty good.
Yeah, so in the first app that we show you today, that whole slack off and pull off weight graph, we invert, so it's inverted so that the beat starts from the bottom all the way, because the highest tension is at when you're bringing in a new drill pipe, right?
Right.
Yeah, so we now use that regular buckling limit formula. So we get the neutral point on the static weight, which is on the drill collar. So the buckling limit calculated will be subtracted from that weight, that neutral point weight. So that's compression. And then the tensile limit is added to that point, and then this is tension.
Okay.
Yeah, that's how we do that.
All right. I am going to send you the targets right now.
All right. No, they're going to send us the coordinates. All right, we're game now, man.
Okay, so you've received the targets, Darlington, is that right?
Yes, I have. We have received it. So we'll start work immediately. Yeah.
Have the other two teams received them yet?
No. So
Miguel, I sent them to you.
Oh, okay.
Ray and Reza. So I'm sending you the. I've muted them already. Okay, so I have the targets, so it's time to work. Because
Okay.
this is real.
I sent them to Benjamin because he's the team lead. Should I send them to somebody else?
Yes, please. We've received it.
To whom?
Pardon?
Who do you want me to send them to? One at a time. Miguel, did you receive them?
Yeah, we can hear you. No
Okay.
problem. Can
All
you
right.
see?
All right. All right. So I need somebody from Ghana to tell me who you want me to send this to, because I sent it to Benjamin and he's not here.
Hello, Fred, I'm here. So we are working on it.
Okay, but I can send it directly to you if you'll tell me who you wanted me to send it to.
Yeah, okay.
Put it in the chat box.
Come again.
Just give me a name that you want me to send it to, or put it in an email in the chat box, whatever you prefer. I don't care. So it's about 8:30, and I will continue to get the targets to the teams in Ghana, both teams in Ghana. Everybody else, we're going to take a break for 30 minutes. We'll start back up at 9 o'clock with the demo. So 30-minute break, return here for the demo at 9.
Hello, Fred. I think we've sent an email. So
Okay.
we're going to receive it. Yes.
All right, I'll get it to you as soon as we finish. Giles, you can stop the recording now and we'll resume at 9 o'clock.
Okay. See you then.
Okay, cheers.